Hello viewers, this is Dr. Jerry's channel. We are going to look at dimension today. In the previous lecture we talked about dimensions, we talked about physical quantities. Today we are going to examine some examples of dimensions, how to write or express the dimensions of different physical quantities. And before I continue, I want you to, when you watch the video, please drop your comment in the comment section, like the video, and of course you subscribe to my channel. So let's move on. So assuming we have the quantity, we have area. We want to find the dimension of area. Area is a combination of lengths. It's a derived quantity which is a combination of lengths. So we express area using the formula, then we get the dimension from that. So we can say area is equal to, we express it in terms of length. We know area is length times breadth, but since breadth is a measurement of length, we are going to make use of length times length. So we say area is equal to L times L. This is the dimension, and so that gives us L squared. What about volume? Volume is equal to L times L times L, and that is L cubed. Then let's talk about velocity. The dimension for velocity, once you know the formula for any physical quantity, you can express that physical quantity in terms of dimension. So velocity is displacement over time What is displacement measured in? Displacement is a measurement of length, so L over T. For acceleration is velocity over time, change in velocity over time. Of course, the dimension for velocity is L over T, so we say L over T divided by time. This is saying acceleration, let's use small letter a, is equal to L over T times 1 over T. That gives us L over T squared, or L T raised to power minus 2. Then let's look at surface tension. What is the dimension for surface tension? First and foremost, get this formula for surface tension. The formula for surface tension is expressed as force over length. Force over length. What is the dimension for force? First and foremost, force is mass times acceleration. Mass times acceleration. The dimension for mass is m, that of acceleration is Lt minus 2. So our surface tension has dimension as follows. Force is mLt to power minus 2 divided by length. And so the length we cancel out, and we have that the dimension for surface tension is m raised to power 1 t raised to power minus 2. Let us look at another quantity, momentum. What is the dimension for momentum? Like I said earlier, these are examples. We're just working on examples of dimensions, how to express the dimension of different physical quantities. We have to know their formulas. So I'm just taking a number of quantities. Then before we go into the next stage of checking different equations to know how correct they are using the concept of dimension. So for momentum, momentum is the product of mass and velocity. Let's say P. Mass is m, velocity is lt minus 1. So it means the dimension for momentum can also be expressed as m raised to power 1, l raised to power 1, and t raised to power minus 1. So I'm going to wipe this off. Then we look at the dimension of other physical quantities. Let us move on. Let's look at impulse of a force. Impulse of a force has formula of force times time. Force times time. Let's call the impulse of a force I. So the dimension will be force. Dimension of force is m l raised to power ml raised to power 1 t raised to power minus 2, and then times time. So this is also, you can express this as ml over t squared times time. This gives us ml over t. And if that is the case, then impulse of a force has dimension of m raised to power 1, l raised to power 1, t raised to power minus 1. So impulse of a force and momentum have the same dimension. Let's look at density, another physical quantity which has symbol of rho. Density is mass all over volume. What is mass? The dimension for mass is m, that of volume is L cubed. So we can either express the dimension of density in this form, or we say that dimension is m raised to power 1, L raised to power minus 3. Let's talk about another physical quantity, work. Work is equal to force times distance. Force times distance. The dimension for force is m, l t raised to power minus 2, then times distance. So work has dimension, let's say W, has dimension of m l squared t raised to power minus 2. Then we look at another physical quantity, coefficient of viscosity. coefficient of viscosity. It's expressed like this. So we say the dimension coefficient of viscosity. What is the formula? The formula is force. We are going to look at two formulas. Force divided by area times velocity gradient. Velocity gradient has dimension of velocity over length. Over length. So its dimension will be that of velocity Lt to power minus 1 divided by length. So which is t raised to power minus 1. So we say velocity gradient has dimension of t raised to power minus 1. We already know that of force and area. So the dimension of coefficient of viscosity will be equal to force is m Lt to power minus 2 all over L squared times what? T raised to power minus 1. We can process this equation further by expressing as this: ml over t squared divided by L squared over t. Which we can further express as ml over t squared times t over L squared, which will give us m all over t times L. And so the dimension for coefficient of viscosity is m raised to power 1 L to power minus 1 t to power minus 1. We are going to look at another formula to also calculate and to express the dimension of coefficient of viscosity. So let's move on. I'm going to wipe this off, then we proceed. Again, we can express coefficient of viscosity as force times length divided by area times velocity. Now, we already know the dimension of the above quantity, so we just simply impute their dimensions. That of force is m Lt to power minus 2 times that of length all over area is L squared and velocity is L over t, or Lt minus 1. We can simplify this further by expressing it this way: m L squared, because times L is S squared, then T to the power minus 2, all divided by L cubed T to the power minus 1, which is ml squared over T squared divided by L cubed over T. We can further express this as ml squared over T squared times T over L cubed. If we simplify further, we have ml because L goes and we have L here. T cancels and we have T here. So you have M over LT. And so this gives us M raised to the power 1, L to the power minus 1, T to the power minus 1. Then let us look at another physical quantity, moment of a force. How do we express the dimension for moment of a force? So we'll say moment of a force this is equal to force times perpendicular distance. Just simply say force times the distance. And our force is equal to ml T raised to the power minus 2 times what? L. So it implies that the dimension for moment of a force is m raised to the power 1 L squared T raised to the power minus 2. We've talked about velocity gradient. Let's look at pressure gradient. Pressure gradient is simply expressed as pressure over length. So pressure divided by length. Pressure is expressed as force over area. So force over area, which is equal to m LT raised to the power minus 2 all over L squared. This gives you m T raised to the power minus 2 over L. So that the dimension for pressure is m L to the power minus 1 T to the power minus 2. Then that of pressure gradients will now be equal to m all over LT squared divided by L, which is the same as saying m over LT squared times 1 over L. And that gives us m all over L squared T squared. So the dimension for pressure gradient, let's say dimension for pressure gradient is equal to m L raised to the power minus 2 T raised to the power of minus 2. So that is the dimension for pressure gradient. I'm going to wipe this off. We'll look at two more or some other physical quantities and proceed. So I'm going to wipe this off. So let's look at the dimension for torque. TORQUE. we have to know the formula, and the formula is RF sine theta. But trigonometric functions are dimensionless, meaning they don't have dimension. So we are going to focus on just R and F. R is equal to radius, F equal to force. So torque, the dimension for torque will now be that of radius. Radius is a measurement of length, so we say L times force, M L T to the power minus 2. So torque has dimension of M raised to the power 1, A raised to the power 2, T raised to the power minus 2. Then we look at Young modulus. Young modulus, which we expressed as y. We use y to represent Young modulus. Subsequently, is expressed as stress all over strain. Stress has the same dimension of pressure. Stress is force over area. So the dimension for pressure, which is the same as that of stress, is M L raised to the power minus 1, T raised to the power minus 2. We have done that before. So then we look at strain. Strain is expressed as change in length all over the original length, that's divided by the original length. And of course, this is L over L, and this is 1. So strain has no dimension. So therefore, Young modulus has dimension of pressure. Since strain has no dimension, we're having 1. So it means that Young modulus has dimension of what? Pressure. So assuming you come across a question that says which of the following quantities have the same dimension as pressure, and you come across stress, which of the following quantities has the same dimension as pressure, you come across Young modulus and so on and so forth, you know your answer is Young modulus. Stress also has the same dimension as pressure. Or we could go another way to say Young modulus is equal to stress over strain. We know this already. Just want to simplify further. And if stress is force over area, you say Young modulus is F over A divided by the strain is change in length all over. This is change in length, please, which is a measurement of length anyway, all over original length. And so we express this as F over A times length all over what? Change in length. Of course, these have the same dimensions. Length, change in length, they have the same dimensions. So it goes away, and you have F over A, which is area. So the dimension for Young modulus is that of pressure. So it makes it much easier. So we are going to stop here for this particular lecture. We've looked at some physical quantities, how to express these physical quantities in terms of dimensions. We've checked a number of them. So In our subsequent lectures, we are going to consider the other importance of dimension, how to use dimension to check if an equation is correct or not, and how to use dimension to obtain a relationship between different physical quantities. So, once again, I encourage you to drop your comments in the comment section, like the video, share the video, and of course, subscribe to my channel so that you can also get more videos. When I upload videos, you get the videos. Once you subscribe to my channels, you get a notification, and so you can follow up. Thank you.